When it comes to running an IGP within your enterprise network, OSPF is the one that you're going to encounter in the wild the most. Why is that? Well, it's kind of a lot of history to it, but the quick answer is that it is scalable as all heck, it is secure as all heck, and it is stable as all heck. Now, how does OSPF actually operate, and how does it ensure that it's scalable, stable, and secure? That's what we're going to talk about throughout this skill. By the end of this skill, you'll understand the inner workings of OSPF and the Dijkstra algorithm, how it builds a shortest path first tree. Then you'll understand things like how you can implement authentication, as well as summarization points within an actual enterprise network. Get ready, because this is going to be a big one, as it's very important for real-world design of OSPF. Let's get going. Very similar to almost every other IGP that's out there, a big part of OSPF is discovering who its neighbors are and then exchanging route information. That's not unlike ISIS or EIGRP, right? But now what we have to talk about is, how does OSPF actually go about doing it? What is the whole designated router and backup designated router thing? These are all very, very important things, and there's some key aspects in order to make your neighbor adjacency actually come to life. That's what this nugget's all about. Let's talk about how neighbor adjacencies are really formed within an OSPF network. So the first thing that we're going to be talking about is how OSPF neighbor adjacencies really come to life. And we've got a very basic topology here on the screen to bring this into point. Now, we're going to talk about a simple point-to-point neighbor adjacency, as well as how an adjacency behaves on a broadcast Ethernet segment. It's very different from one to the other, as long as you configure it that way. And later throughout the skill, we're going to talk about the implications of when we bring up these types of adjacencies together, but that's a little bit beyond the scope of this particular nugget. This nugget is going to be all about how a neighborship is actually formed and what parameters are needed to do that. So let's introduce you to the topology real quick as we traverse through this particular skill, and then we'll actually start bringing OSPF neighbor adjacencies to life. I'm first going to focus in on this particular link right here, Ethernet 01 and Ethernet 00. This is going to be a point-to-point link because there are no other devices on this particular network. Now, why is it a point-to-point link? That's going to be coming up in another nugget. What we're going to be doing now is just establishing a point-to-point link and talking about the OSPF adjacency state machine. Now, this is a phrase that you're going to see a lot as you go through your either CCNP or even CCIE level studies, is state machine. Whenever you see state machine, you should just be thinking of this particular protocol or whatever we're talking about is going to go through a series of states before it comes to the fully completed or fully converged state. So what we're going to be talking about in this nugget is what are the states that a neighborship will go through before it becomes to the final full state. Here we go. I'm going to bring up Secure CRT, and we were looking at the link between R2 and R3. So let's take a look at R2 real quick. I'll give it a show IP interface brief, and you can see we've got some IP addresses here. Now we've got 192.168, and the third octet represents the names of the routers that we're actually going to be working with, R2 and R3. So when I see 192.168.23, that's how I know it's R2 and R3's link. Over here, we've got R1, 2, and 4 on the broadcast segment. Beyond that, I also have a loopback address, and this is actually going to be a pretty important part to how OSPF operates, is when it comes to the router ID. Now, again, I can't stress this enough. As part of the ENSLD preparations, if you're here because you're preparing for the ENSLD exam, you don't necessarily need to know the commands, but if you're going to be learning these things, it does help to follow along or at least practice them in order to solidify those concepts. So if you don't necessarily want to learn these commands, don't feel like you have to type these commands in your own lab environment, just follow along and try and understand the big thing, which is the adjacency state machine. In order to enable OSPF, there's a couple ways that I need to do it. First, I need to turn on the OSPF process and just give it a arbitrary process ID. Like 1. This 1 doesn't really mean anything. It's only locally significant to this particular router, router 2. On the next router, I could put something like router OSPF 49 and it wouldn't matter. So by typing this, I've now enabled the OSPF process, and the next thing we have to do, and this is very, very important to understand, is that we have to enable OSPF on interfaces. This is where it can be kind of confusing, because from here, we can type the network statement and specify network 192.168.23.0 and use a wildcard mask like 000.255. You gotta think about the essence of a wildcard mask. What the wildcard mask is really trying to do here is it's trying to match any bits, whether subnet bits or host bits, in order to match an IP address on an interface. It's trying to find IP addresses based on what could be listed in this wildcard mask. So when we type this in, it's going to find this IP address as matching as its host bits, and it's going to be enabling the OSPF process on a matching interface. It's not enabling it for an entire network. It's enabling it for a matching IP address on an interface. That's very important to understand how network statements actually work in Cisco's IGP world. But beyond that, we also have to specify which area OSPF is going to be operating in. Now, we do have a nugget coming up later that goes over what areas really do and how areas can help you scale. For now, it's best to just put things in area 0 and then talk about what those areas do later. But this is a major talking point about OSPF and how neighbor adjacencies form. When two devices are trying to form an adjacency to each other, what's going to happen? Actually, let me bring up the diagram real quick. R2 will start sending hello packets, and those hello packets will contain very important information that has to match on both sides in order for an adjacency to come to life. One of those things is the area. So if I type area 0 right here on R2, in order for an adjacency to come to life on R3, it also has to be in area 0. Beyond that, some other things have to be considered here. An area type. Again, don't worry about the area type so much. We're going to be talking about the area type in an upcoming nugget. I also need to make my E's look more like an E. They also have to agree on hello and dead timers. So let's talk about hello and dead timers for 1 second. When these two adjacencies come to life, they have to know how frequently am I expecting to receive a hello from you, and if I miss so many hellos, when do I declare you as a dead neighbor? In this case, the default for OSPF, the hello timers are sent every 10 seconds on an Ethernet segment, and the dead timer is multiplied by 4 or 40 seconds. Now, if we're working with a non-broadcast multi-access network, this has moved up quite a bit. This moves up to every 30 seconds for a hello timer and every 120 seconds for a dead timer. Since we're only operating on Ethernet and we're not adjusting the dead timers at this time, we can expect the hello packet to carry a hello timer of 10 and a dead timer of 40. And as long as we don't alter it on R3, it'll be sending a 10 and 40 back as well. Now, there's some things that should not match as well within the hello packet. Each router, when a neighbor adjacency is coming to life, they have to uniquely identify themselves to the world. This is using something called a router ID. And the router ID can come from 3 different places, and this is very critical to understand. The first thing is that we can explicitly set the router ID on our router. So if I actually jump back to the configuration here, before I enable the network statement, I'm actually going to type router ID and type in something like 2.2.2.2. Jumping to R3 real quick, I'll go into configuration mode, router OSPF, and like I said last time, this doesn't matter, I'll type in 49, and I'll say router ID 3.3.3.3. OSPF has to know about all of the routers within its area, and the router ID is what uniquely identifies it. To really understand why it's important that all of the router IDs be uniquely identified and each router is uniquely identified, you really dig into what is the difference between distance vector and link state protocols in the first place. A distance vector protocol is not unlike this sign right here. All we know is that the next city is 76 miles ahead. We don't know much about that path. But we know, based on our calculations in a distance vector protocol, like RIP, or like a hybrid protocol like EIGRP, we know that as long as we send the traffic in that direction, it'll eventually get there, and that's the quickest way there. This is really about it. You're at a sign in the road that just says go in that direction, and that's how far away it is, and that sets up what a distance vector protocol does. Whereas OSPF knows about every single road that there is in the entire map. And the roads, in this case, are kind of like routers. We have to uniquely identify each road and then look at how much time or how much traffic is on that road in order to know what's the fastest way there. That's what the Dijkstra algorithm does. That's what the shortest path first tree does, is it takes every single bit of information on this entire map or our entire topology, and it finds the fastest way there. But in order to do that, our routers have to uniquely identify themselves and then say, these are our connected routes. That's what OSPF does at the end of the day. So when we look at this topology right here one more time, what we're really seeing here is router 3 will advertise itself to the rest of the devices in this environment and then say it knows about these roads and how much it costs to get to them. So when it comes time for router 4 to calculate its paths there, it knows, okay, I've seen all of the advertisements from all of the routers basically saying I have the entire map with me here. I now can find the fastest way there, and it looks like the fastest way there is coming from my router ID buddy over here, 3.3.3.3. Now, I did say that there are 3 ways that the router ID can come into existence, didn't I? The first one you've already seen, where we explicitly set the router ID, and that is the best practice to do, is to explicitly set the router ID. But if you forgot to set the router ID, the next thing that it falls back to is the highest loopback address. Now, why is this important? Because if we assign a loopback address, say like I did right here on these devices, if I say do show IP interface brief, and also clean up my screen just a little bit, we can see I've got a loopback address here of 2222. If I look over here on router 3, I didn't assign a loopback address, but luckily I did assign a router ID, so I don't have to fall back on that loopback address. Again, why is it important? If I didn't explicitly set the router ID, it would fall back to this loopback address of 2222. But then let's say I come along one day, and I create a new loopback address, and I say the IP, the IP address is 22.22.22, 255.255.255.255. Now that I've got this new loopback address, I can give it a do show IP interface brief, and we see now I've got a 22.22.22.22 address. All of my neighbor adjacencies would still see the old one until something happens. If this router goes down or reboots or something like that happens and it reconverges OSPF, a new router comes into play, and now everything is going to be based on the highest loopback address, 22.22.22.22. So if we're ever expecting to change our loopback addresses, this is why we go with the router ID to keep things nice and consistent. But then there was that third option, right? If we didn't have loopback addresses and we didn't explicitly set the router ID, let's say here I type in no router ID 3.3.3.3. So now my device does not have an explicitly set router ID, and it does not have a loopback address. It then defaults to the highest physical IP address on the network. So in this case, I don't want to do that. I want to keep my router IDs alive. And up to this point, we've talked about how the area number has to match, like area 0. The area type has to match. Basically, this is saying, is this going to be a stub area or a not so stubby area? And we're going to talk about that later. They have to match on the hello and dead timers. But then when it comes to the router ID must be unique for every adjacency within the entire topology. So that's kind of one that throws you for a loop. Other things that have to match in order for this adjacency to come to life is the MTU. They should know how much data they can send within a packet. If we don't have matching MTUs, it will get stuck trying to come to life as it's trying to exchange data about the routes to each other. And then the last thing that has to match here is the actual subnet that is in action itself. These two devices have to agree that they're talking on the same subnet because of how creating that map actually works. They have to agree on what network they're actually speaking on, and then what networks or routes they can transmit over that. So we have a lot of things that have to match: area, area type, hello and dead timer, MTU, and subnet, and then one thing that cannot match, which is the router ID. So it's time to actually bring this adjacency to life real quick. I'm going to do this in 2 different ways. On router 3, I'm going to specify the network statement 255, specifying the wildcard mask that will match on this particular host, and I'll say this is going to be in area 0. Right now, R3 has started sending out hello packets towards R2. If I actually capture on Ethernet 00, we can see the Wireshark capture of the hello packets coming to life. Here comes Wireshark. I'll filter by OSPF, and there I already see the first hello packet going across the wire. Do you see this information? The network mask, the hello interval, the dead interval. The actual OSPF header itself contains the router ID that's being spoken here. And it's worth pointing out immediately, what are we talking on here? Because we're speaking on a broadcast network, it's sending out multicast packets destined for 224.0.0.5. This is the multicast address that OSPF routers speak to when they're trying to form a neighbor adjacency towards any device that could be listening on this particular Ethernet segment. Again, notice these timestamps here. They're about 10 seconds because that's the hello timer that was default on an OSPF interface. So now if I jump over to router 2, let's do this. Let's go into interface Ethernet 00, or 01, I should say, and let's bring OSPF on directly on this interface instead of specifying a network statement. From the interface, I can say IP OSPF. I specify the process ID, which was 1, and then my area number, which was 0. The area number, again, has to match. The process ID is completely irrelevant. I press enter, and at this point, the OSPF, look at how quickly it came to life right there. It went from loading to full. And see all this information that now shows up and was transmitted back and forth to each other? This is actually pretty interesting. Once the traffic was discovered going from one device to the other using multicast, and they discovered each other, they moved to unicast packets. When they're speaking in unicast packets, that means the state machine building the adjacency state has begun. The state machine moves in this order. Both devices, actually let me write them like this. Both devices begin in a down state. They are trying to find hellos or trying to find their neighbor. A hello packet gets sent from router 2 towards router 3, who receives the hello packet. Router 3 sends a hello packet back, but a very important characteristic of this hello packet is it contains routers seen. And it would say, I've seen router 2 on the specific interface. When router 2 receives this packet, it knows that it has sent a hello packet and it has reliably received itself back, meaning it knows that R3 has seen me, and it's time to start initializing our database exchange. Now, because the state machine takes up a lot more space on my drawing board, I've actually hidden my head at this point so that we could talk about how it moves on past this phase once we start sending hello packets to each other, and we've now seen ourselves once we start sending hello packets to each other. When we start sending hello packets back and forth, we move from the down state to the init state. We are now trying to initialize the OSPF process, and this is where we're sending these hello packets back and forth. And what we're looking for is when we receive a hello packet, has the other router seen ourselves? Because we're going to be looking for this router knows about us and we know about them. And from there, once we've seen ourselves and a hello packet has basically made itself round trip, we move into the two-way state. The two-way state on both sides means that we have seen ourselves through the usage of our hello packets, and we are now ready to start the exchange of OSPF information. The big thing here in the two-way state is we determine whether or not we are on a broadcast network or a point-to-point link, and whether or not we need to perform a designated router election, or if we should even form a neighbor adjacency with this neighbor. Now here's the big kicker. We're going to talk about designated routers and backup designated routers in the very next nugget. One of the things, though, is if R2 here is trying to make a neighbor adjacency to R3, and we find out that R3 is neither a designated router nor a backup designated router, and an election has already taken place, this state will stay in the two-way state. That's actually a really big talking point that we'll talk about more when we talk about the designated router and backup designated router election. For now, let's just proceed because these are the only two routers on this Ethernet segment. So after they agree that there is no other designated router or backup designated router within this segment, they will start exchanging information with each other. And this is how it moves into an exchange section that begins with the X-start state. In the X-start state, these two routers, R2 and R3, are going to agree on who gets to go first, who gets to ask for routes first. They have an election that takes place between these two routers to see who can actually request information first. This can be manipulated by the OSPF priority, much like other things that you're going to find out, like the designated router, or it can go based on the router ID. And in a lot of ways with OSPF, the highest number always wins. So the higher the priority or the higher the router ID, that person will get to go first, so to speak. These two routers will exchange database descriptor packets or database descriptions that define what routes it knows about in its OSPF database. And at this point, it will move on to the exchange state, where they are exchanging what routes they know about with each other. The router that was elected first, or the router that was elected as in control, will get to ask the other router for any LSAs or routes that it doesn't know about. And when it makes that request for the routes that it doesn't know about, it will move into the loading state, because it is loading routes from the other router. And once it has loaded all of its routes, then this router will go into the loading state, and it will look at the database descriptor that has been sent to it and say, I don't know about these routes, let me request those. Once all of the routes have been sent back and forth, it moves from loading to full. When we take a look back at the Wireshark capture again, look, we see the hello packets where we were going through the discovery phase. We sent it to the multicast address. Then we discovered each other and started talking a unicast language. From there, look at that. It went to the database description. It basically says these are the routes that I know about. If we go into the OSPF description, it's basically saying we're about to start the database description process. Then when we get to this packet here, look at this. It starts sending summaries of the LSAs that it knows about. Basically summaries of the routes that it knows about. From here, we can see router 2 made the first request for the routes, and then it received updates that actually contain the actual payload of routes itself. And then lastly, it ended up with the acknowledgement saying that I received the routes. From there, it goes to the full state. So this is how an OSPF adjacency comes to life, just going through the state machine. Very important to understand what the steps are and what are the actual pieces that must match on both sides, as well as the pieces that can't match on both sides. Now, in the next nugget, what we're going to do is we're going to talk about what happens when there's more than one router on the same segment. This is going to be when we're talking about the designated router or the backup designated router. I know this was a big one, but it's a lot of important stuff, and it's very fun to really master the inner workings of OSPF. I hope this has been informative for you, and I'd like to thank you for viewing. All right, I know that was a big one, talking about all of the inner workings that actually bring an OSPF adjacency to life, but it is very important to understand in order to actually troubleshoot what happens in the real world when an OSPF adjacency isn't coming to life. But now we need to talk about another peculiar scenario, and that's what happens when OSPF neighbors try to form on one large Ethernet segment. Basically saying what happens when it's not a point-to-point link. This is one of the design implications of OSPF that actually helps make OSPF more stable and secure. What we're talking about here is the designated or backup designated router. Let's get going. So in the last nugget, we actually formed a neighbor adjacency between router 2 and router 3. Remember this little segment right here? There's something interesting that happened, though, behind the scenes that we didn't really talk about. There was an election that took place to determine who would be a designated router and who would be a backup designated router. And this doesn't really matter when it comes into play on a point-to-point link, but it does come into play on, say, the other segment that we have here, where we have 3 or more routers on the same segment. So what we're going to do is we're going to talk about what did this really do behind the scenes. Check this out. If I do show IP OSPF interface brief, see this little thing right here? The state, this tells me this is the backup designated router on this particular segment. Another important thing that I can do is I can check out my show IP OSPF neighbor output, and it says I have a full adjacency to 3333, who is the designated router. These are very important commands to know and very important commands to understand. Why did this really take place? What's really going on here? What's really going on here is a behavior of OSPF. When OSPF sends a route, what it's really doing is it's sending a link state advertisement. Basically, it's advertising the fact I know about this link that exists somewhere in my topology. Remember, it's kind of like the roadmap, where the router knows about every single road that's available to it in the entire topology. So it advertises its own directly connected routes, as well as all of the other routes that it's learned from each other. Now, this isn't a big deal on this particular environment where we have, 5 or 6 links up and running here. They can advertise 5 or 6 links from one router to the next. But what happens when I have hundreds or thousands of routers? All of a sudden, we've got a major scale problem, because every single router is going to advertise every single link in the topology from one to each other. But wait, there's more. If I do show IP OSPF database, you'll see something pretty important right there, and that's the age. Check this out. If I run this command one more time, see how the age is changing? It's getting older every time I run this command. Basically, what we're saying here is that OSPF LSAs can go stale. So the default behavior of OSPF speaking routers is that on an interval, every so many minutes that we can either manually set or let it default handle, it will re-advertise all of the LSAs within its database. This is called OSPF, or sometimes just SPF, or sometimes LSA. It all leads towards this one important word, flooding. Every router floods its LSAs in every direction on an interval. And when you have hundreds or thousands of routers in your environment, all of a sudden you're using a whole lot of bandwidth and even a whole lot of CPU cycles on maybe sending out LSAs that we already know about, or recalculating the SPF algorithm to find the shortest path somewhere. This isn't also even talking about when a link goes down and then we have to resend packets out to everybody else, updating them, letting them know that a link has changed or flapped or something like that. This is just happening by default on an interval. So one of the ways that OSPF actually helps us by default is on a big Ethernet segment like this. When we enable OSPF on this Ethernet segment, it will form neighbor adjacencies to each other, but it doesn't necessarily form a full mesh, and it doesn't necessarily send all of the LSAs to all the different routers. You see, these routers can recognize, hey, wait a minute, I am on a Ethernet broadcast segment. And when it discovers that it's on an Ethernet broadcast segment, it first sends hello packets to 224.0.0.5. This is so that it can discover its neighbors. But when it receives responses back from more than one neighbor, it knows that we are on a multiple segment Ethernet link. So OSPF then goes through an election process to see who is going to be the designated router and who is going to be the backup designated router. The role of the designated router and the role of the backup designated router is they will be the two routers who are responsible for flooding all of the LSAs on a link. So instead of R1 flooding all of its LSAs, then R4 flooding all of its LSAs, then R2 flooding all of its LSAs, only one router will be the designated router responsible for sharing information to all of the other routers in the environment. It works in a lot of ways like the way the exchange worked, based on priority or based on highest router ID. For instance, router 4 here has a loopback address of 4.4.4.4, or we could set explicitly the router ID of 4.4.4.4. And when all of these devices start trying to discover each other, they'll see that router 4 has the highest router ID of 4444 as opposed to 1111 or 2222, and they'll decide that R4 will be the designated router. So R1 will form a full adjacency to R4, and R2 will form a full adjacency to R4. They'll go through the exact same state machine process. That way R4 learns about all of the links within the topology. And then R4 will be the one that floods these links to all of the devices. So maybe we add routers into the segment here. R4 would be the one that's flooding those to all of those devices. If R1 has a change in its environment and it needs to update all of the routers in its environment, it will only send the update to R4, who would then send it back out to all of the other devices. Instead of flooding all of these routers and receiving all of these acknowledgments back, it's just going to send it one time to the designated router, who's going to handle the rest of it for us. This is a big scale improvement because now all of the routers only need to form full adjacencies to the designated router and the backup designated router, and then only one LSA gets flooded from the designated router. Now, I did mention there's a backup designated router. Basically, 222 here would be the backup designated router, and it's just checking to make sure that R4 stays alive. R1 in this case, if I clean up the screen just a little bit here, R1 in this case will form a full adjacency to R4 and to R2. But if we were to add in more routers right here, R1 would notice that these other routers exist, but it would not form a full adjacency to them. It would only form a full adjacency to the designated router and the backup designated router. So with that being said, let's see it in action. On R1, I'll go into router OSPF1. I'll explicitly set the router ID to 1.1.1.1. And I'll say the network is 192.168.124.0.0.0.255 and area 0. I'm just going to copy this command real quick for simplicity's sake as we move on to router 2. I'll go into router OSPF1, paste this in, and then I'll enable it on router 4. I'll go into router OSPF1, specify the router ID of 4.4.4.4, and then paste in my network statement. And there we go. After a second, the OSPF adjacency comes to life. It does take a little bit more time to get these adjacencies to come to life when they're on a broadcast segment because it is going through the designated router selection process. In fact, if you notice the order that I actually completed these in, I did router 1 first, then router 2. Those two had already started exchanging packets when router 4 entered the mix. Because they weren't already in a full state, it all had to start over again and go through a designated router election process because they're like, wait a minute, we have somebody else on this segment too. Because we have more than a couple devices, we need to go through the designated router process. So if I do show IP OSPF neighbor from router 1, I see that R4 did in fact become the designated router because it had the highest router ID, and router 2 did become the backup designated router. Now to have some real fun with it, I'm going to add a node to the topology. We'll boot it up, and then once it gets booted up, I'll enable OSPF on it, and we'll see what the adjacency state looks like between router 1 and router 6. So here we go. I'm now on R6. What I'm going to do is I'm going to go into router OSPF1. I'm going to specify the router ID of 6.6.6.6. Again, keep in mind, this is pretty important, that an adjacency is already brought to life at this point. So there's not going to be a new designated router election because an OSPF designated router has already been elected. The only way that 6.6.6.6 would become the designated router is if the OSPF processes were restarted across the entire topology. I'll go into interface Ethernet 00. I'll give it an IP address on the network, 192.168.124.6, 255.255.255.0, no shut, and I'll say IP OSPF1 area 0. Very important syslog message just happened right here on the screen. Neighbor adjacencies with 2222 and 4444 went from loading to full. R1 did not go from loading to full. There is no neighbor adjacency with 1111. See, if I type in to do show IP OSPF interface brief, whoop, gotta type it right, it tells me we are running OSPF on this interface, but we are not a designated router or a border designated router. We are in the DR other state. Beyond that, if I do show IP OSPF neighbors, there we go. There's the magic right there. We see our designated router is 4444. Our backup designated router is 2222. And we only remain in the two-way state between R1 and ourselves. So whenever we have a link state update, whenever R6 has a link state update here, it's going to send it to its designated router and its backup designated router now on a new multicast address, 224.0.0.6. Neighbor-to-neighbor connections happen on 5, but neighbor-to-DR or BDR communications happen on 224.0.0.6. Once this has been received and acknowledged by R4, it will send it out to all of the rest of the devices on this particular topology. So that's understanding how OSPF does help us scale, and it limits some of the problems with SPF flooding when it comes to working on an Ethernet segment. I hope this has been informative for you, and I'd like to thank you for viewing. Now, I'm going to be honest with you, when I was first learning about networking and I was first learning about OSPF, I really kind of dazed off when it came to learning about the OSPF LSAs. Here's the big spoiler. Here's the big secret. Shh, are you ready for this? Are you ready for this? In order to get to the expert level with OSPF, the thing that you need to learn more than anything else is the LSAs. The LSAs are the behavior of OSPF. And when you can learn what the LSAs really truly do under the hood, you can then learn how to manipulate the LSAs. This is where we can actually take OSPF and start performing traffic engineering. This is where we can actually manipulate how our OSPF topology and areas are designed. It all starts with the LSAs. My point to say is that when we cover the LSA content, this is actually the most important content that there is, and it is also the most empowering content that there is when it comes to learning OSPF. So without further ado, let's cover the OSPF LSAs that you would typically see in an enterprise environment. Now it's time to talk about the most powerful part of OSPF, and that's the link state advertisement, the LSAs themselves. This is how OSPF actually determines how OSPF should work. This is how you can actually begin to manipulate how OSPF behaves too. So it's really critical to understand how OSPF and the LSAs operate. There are many different types of LSAs, some of which, actually most of which, or about half of which, aren't even present anywhere within an enterprise. They're actually leveraged by service providers. But what we're going to talk about today is going to be the LSAs type 1, 2, 3, 4, 5, and 7. The LSA type 1 is known as the router LSA, and this is really the beating heart of OSPF. Every router will advertise a type 1 LSA when it comes time to actually advertise who they are, as well as what links do they have that they know about, that they're connected to. In this case, R1 would say, I am 1.1.1.1, that's my router ID, and I know about this link right here. I am directly connected to this particular link. It will send that LSA, in this case, to the designated router because this is on that particular segment, or the backup designated router. And as we know, the designated router will send it down to every device within this particular segment. If we fast forward a little bit and look at R2, R2 will also send R1's LSA to R3 completely unchanged. Because of that, R3 knows that it can get to R1 because R2 also sends its own LSA to R3. R3 can put all the pieces together and see like, oh, I know you have this link, and R1 is also on that link, but it has other links, so it can get to it that way. That's how the SPF algorithm is actually working under the hood, is by forwarding these type 1 LSAs. Now, the type 2 LSA is what occurs on a broadcast segment. This is called the network LSA, and this really identifies who the designated router or the backup designated router are and what are all of the links that it knows about within this particular segment. You can actually manipulate the links like this one right here, and tell it you are actually a point-to-point link so that it doesn't actually use the network LSA at all. See, if I jump over to R2 real quick, I can go into interface Ethernet 01, and I can say IP OSPF network point to point. Notice we receive a mismatch message from R3 saying like, hey, we've noticed that this network type doesn't match, but the neighbor adjacency still comes up. Jumping over to R3, I can go into interface Ethernet 00, and I can say IP OSPF network point to point. It bounces the adjacency again. But now when I do show IP OSPF neighbor, look at that. We no longer have a designated router or a backup designated router section here. This actually eliminated the type 2 LSA on that particular link, and that's one less LSA that we have to flood through our network. So it actually is preferable in a design standpoint to use point-to-point network types whenever we can in order to eliminate the LSAs that are unnecessary within the topology. So the router LSA identifies the router itself as well as all of its attached segments. The network LSA is really used by the designated router to identify who the designated router is on a particular segment, as well as all of the routers on the same Ethernet segment. The third LSA is going to be the summary LSA, but it's not actually doing link summarization or network summarization. What this really does is it comes into play when we start talking about areas in the next nugget. The gist of it is that rather than flooding all LSAs throughout the entire network, we can break our network apart into areas and only send summaries of what took place in an area into the next area. That'll make more sense when we talk about areas in the next nugget. It's very important to know, though, that the majority of the work that we do, of the engineering that we do, happens around the border of one area to the next and takes place with how we manipulate the summary LSA. The Type 4 and Type 5 LSAs are all about route redistribution. And to set up this discussion, I've added one more router here, router 7, into the mix. And right here on this link, they are running EIGRP. I've performed route redistribution to get these EIGRP routes into the OSPF domain. So router 4 now sees EIGRP learned routes from OSPF. A very important talking point is looking at R6. On R6's Ethernet 00 link here, it's running OSPF. On Ethernet 01, it's running EIGRP. And it brought the EIGRP routes into OSPF like this. In other words, R6 is what we call an autonomous system boundary router. OSPF is considered an autonomous system in this section, and EIGRP is considered the other autonomous system. And R6, because it's on the boundary of both of these autonomous systems, becomes an autonomous system boundary router. The Type 4 LSA is what is used to signal how do we get to the closest autonomous system boundary router for a specific link. The Type 5 LSA says, what are the external routes? You can see how these two are used together. R4 will say, okay, I know about this external route thanks to the Type 5 LSA, and I know how to get to that route thanks to the Type 4 LSA that identifies where my autonomous system boundary routers are. You have to think about a large topology that may have multiple ASBRs, and we could manipulate the traffic in order to get to either the closest ASBR so that we can get out of the OSPF domain as quickly as possible, or we want to get to the ASBR that's closest to the destination. This is how the engineering comes into play, and that's the type of stuff that you get into when you get to the expert or CCIE level. Now, lastly is the Type 7 LSA, and this also identifies external routes, but it does this in a not-so-stubby stub area, which is what we're going to talk about in the next nugget again. Know that there's not much difference between the Type 5 and the Type 7 LSA outside of just what type of area do these occur in. Now, when you want to see these LSAs in action, if I go and bring up router 3, for instance, I can give it a show IP OSPF database, and here we go. I see my router LSAs. Those are my Type 1s. I see my network LSAs, those were my Type 2s, and then I see the Type 5 LSA. This is the external link. You may be going, wait, where is the ASBR here? Well, we already know how to get to 6666 or the advertising router, so we don't actually need that LSA. But if we were going into a different area, that area would need to know how to get to the autonomous system boundary router, and that's where the Type 4 comes into play. We're going to talk about that more in the next nugget. Trust me on that one. That'll make more sense when we start talking about dividing and scaling our areas up. But also notice that these LSAs are specific to the area that they're participating in. Routers can participate in more than one area. So when you look at the database, you need to look at, okay, these are my Type 1 LSAs that exist in Area 0. So get to know these LSAs and memorize them inside and out, because when we get into the next nugget and you see how we can break apart an OSPF domain into areas, you can then start to see, oh, that's where the LSAs really come into play. This was just setting up the discussion for areas, because when it comes to areas and the LSAs, that's really how you manipulate and engineer OSPF. I hope this has been informative for you, and I'd like to thank you for viewing. Now it's time to talk about scaling OSPF. You see, the more routers you have, the more routes you have. And here's the thing about OSPF. On an interval, OSPF-enabled routers will flood all of their LSAs throughout the network again after a certain time. It's basically like a refresh timer. And sometimes this can force the SPF algorithm to be rerun on each of the devices throughout the topology. The point is that the more routers you have, the more flooding you have, and then the more calculations you have, and all of a sudden you run into a CPU cycle and a bandwidth utilization problem because you have too much OSPF running in your area. So what we can do is we can break apart our OSPF sections into areas, and in this nugget what we're going to do is we're going to introduce how areas within OSPF really work and some of the added benefits that actually come with it, like summarization. Let's get going. So now it's time to talk about areas, which is the big design point when it comes to designing an OSPF network. The idea with areas is that we have all of these routers. Maybe here we've got 1, 2, 3, 4 routers, and then we've got this external router here. What happens if we had, let's say, more than 4 routers? Let's say we had 500 routers. Think about it again, how OSPF works and how those LSAs behave. Every LSA Type 1 and 2 is going to be sent throughout that entire area. In our case, we called it Area 0. And it's going to be flooded on an interval. So much bandwidth is going to be dedicated towards flooding all of those packets, those link state advertisements to each other, and then recalculating the SPF algorithm when it happens, that it actually becomes a major scale issue. So what we can do is we can start to break apart our OSPF domain into separate areas. So let's say we wanted this to be an area here, and then we wanted this to be an area here. We have a separating line right here on R2. What's really important about this, and especially OSPF and link state databases, is that all routers in the area have to agree. They have to have the exact same database. That way they can all calculate the best path to get from point A to point B and to ensure that it will be a loop-free topology. That's what really makes the link state database work. I mean, could you imagine if I had a map of, say, Baton Rouge, Louisiana here, and my wife had a completely different map of Baton Rouge, Louisiana, and we were trying to get to the same place? We might never get there. We might just be driving in circles, and that's kind of the point. That's kind of the point, that the area all has to be matching within each other. But when we break apart areas, let's say we have area 0 here and area 1 here, Area 1 doesn't need to know every single detail about Area 0 anymore. It needs to know what routes exist in Area 0, but it doesn't really care about the actual topology or the database itself. It just needs to know, if I want to get to something in Area 0, I just need to punt it to this router here, and that's where it goes from there. This creates a significantly smaller or simpler link state database to manage, and that's why that was called a summary LSA. If I'm cleaning up my screen just a little bit here, R2 becomes what's called an area border router. It has one leg in Area 0 and one leg in Area 1. And as traffic or as routes are learned from Area 0, it will put each one of those routes into its own Type 3 LSA and send the LSA into the next area. So if I'm jumping onto the command line real quick, I'll say no IP OSPF 1 Area 0 on that particular link. And now I'll just change this to be IP OSPF Area 1. On router 3, we know that the area has to be a match on both sides or this adjacency won't come to life. So if I go into router OSPF, so if I do show run section OSPF, I see this was router OSPF 49 was the process ID. And I'll say no, highlight this real quick. And network. Oh, see, there's the dead timer just went down. 40 seconds must have passed because that was the default dead timer, right? I'll now paste in my network statement, but change the area to Area 1. And in just a second, there we go. The adjacency comes back to life. Now check this out. If I do show IP OSPF database, look at this. I see my router advertisement, my router LSA from router 2, but then it jumps straight to the Type 3 summary LSA. Recall there's no Type 2 LSA because in the previous nugget we made it a point-to-point link. So it jumps straight to the router 2 LSA where it learned about the 192.168.124 network. Beyond that, jumping ahead a little bit, we see the Type 5 LSA that was brought in, which was that external network, and it's asking, wait a minute, how do I get to the ASBR because I don't know about this? And now we see the summary ASBR, the Type 4 LSA. So we have Type 1, 3, 4, and 5 now in the link state database in a different area, and it's a significantly smaller database. Then if I were to jump to R1 here and say show IP OSPF database, see, we have all these Type 1 LSAs here, a Type 2 LSA. We learned about a summary address from Area 1, and then we have the Type 5 LSA. So we've significantly reduced the size of our database in one of the areas because we can now break apart the OSPF domains into different areas. Here's the real spoiler. Here's how it would really look in an enterprise. Yeah, it was only a matter of time till I jumped back to this diagram, right? We saw this maybe already in the IPv4, IPv6, and ISIS nuggets. Now we're seeing it in OSPF. And you can see right here at my distribution layer, this is where the area border routers, or in these cases really layer 3 switches, are going to reside. They have one leg in the core and one leg in their own areas. It's also up here too. This also becomes a very important design consideration within OSPF. OSPF must have an Area 0 backbone. So let's say traffic wants to go from Area 2 to Area 1. In order for that to happen, it must traverse through Area 0 in order to get to it. Area 0 must exist as the backbone area or the transit area by rule, by default, by law, in an OSPF network. So this is how the enterprise network would be laid out and designed within an OSPF area, or rather an OSPF domain. This also introduces an interesting point. Maybe we've subnetted this 192.168.2 all the way down to something small like 28s or 29s, and as traffic arrives at the area border router, not only does the area border router send in the type 3 LSA, which is called a summary LSA, but it can also perform actual route summarization at this point. So it doesn't have to send in every single prefix from one area into the other. It could actually summarize it as it goes out of the area into the other. But here's the thing, we can't summarize within the area because, again, every single device must have the exact same database within for each of the LSAs. So as we change areas and kind of move into a different database, that's when we can perform summarization and filtering. But this is where it gets interesting, and this is where we start talking about the different area types, because we've talked about how the different LSAs work. Now we can actually talk about how we can manipulate the area itself. Pretend for a moment that up here on switch 20, this was actually connected to a large EIGRP autonomous system. I'm going to write EIGRP right here. And we redistribute EIGRP in right here on switch 20. We know that switch 20 becomes the autonomous system boundary router, and now type 4 and type 5 LSAs will be flooded throughout the network. Specifically, our area border routers will be the only places that type 3 and type 4 LSAs are originated. The type 5 LSA will identify all of the external routes that are being sent. But take a look down here on area 1 and area 2. Their only way to get up here to this EIGRP domain is through the core. They only have one exit point to get to that. Is there any reason whatsoever that they need to have all of these external routes in the first place, or even an ASBR? No, their one path up to EIGRP, they only have one way, and that's through the core. So we can manipulate this area right here such that no type 4, 5, or 7 LSAs will ever be entering this area. Instead, it could receive just a default route. What we're talking about here is the stub area. The stub area says, I don't really care about learning all of those external routes since I only have one way to get to them in the first place. Keep in mind that type 1, 2, and 3 routes will still enter this particular area. So any routes that actually were originated from area 3 here in the 192.168.3 domain, those routes will still make its way down. That brings up an interesting point though. In order for area 2 or area 1 to get to area 3, it's still only one route forward. It still goes through the core. So do we even need to get those type 3 LSAs? We really don't. We could also replace those type 3 LSAs with a default route, and that is a total stub area. In a total stub area, only the type 1 and type 2 LSAs will be sent throughout the network. Everything else is sent as a default route through the core, or the transit in this case. Do you start to see how the understanding these LSAs plays a pretty important factor? Now, all of a sudden, we're limiting our flooding of these LSAs throughout the network. They get stopped at the border. When we say this is a stub area, or a total stub area, we're basically saying we don't care about external routes, or we don't care about summary routes because we've only got one path to get to them in the first place. And keep in mind, all the way back to that very first nugget about neighbor adjacencies, for a neighbor adjacency to actually come to life, they have to agree that we are a stub area because we have to agree about the contents of our database in the first place. Now, I did mention there was one more LSA, the type 7 LSA, and that's where we say this is going to be a stub area. We don't want type 4 or type 5 LSAs, or maybe even type 3 LSAs to come into play, but I might perform redistribution from BGP or ISIS into this particular area. When all of these devices in here agree that they are a stub area, but we do want to perform route redistribution in this area, it becomes a not so stubby stub area. At this point on switch 7, a type 7 LSA will be generated, and all of the devices in this area will see that there is an external route learned from OSPF. Note, there is no type 4 or type 5 LSA still in the area, but we are allowing a type 7 LSA. At the point that it gets to the area border router, the type 7 LSA is translated into a type 5 LSA, and it does forward the type 4 ASBR LSA throughout the rest of the network. So these are the area types in an area design, how we can actually break apart the OSPF database and help it scale a little bit beyond that, adding in area types like stubs, total stubs, not so stubs into the mix as well. So that's been understanding the area types of OSPF. I hope this has been informative for you, and I'd like to thank you for viewing. Now, we've talked a lot about OSPF scalability and stability up till this point. Now we have to talk about security, and sure enough, just like every IGP, OSPF gives us the ability to use authentication on each one of our links within the OSPF domain. So let's talk about how we can use authentication, whether plain text or with some form of hashing algorithm in an OSPF area. Let's get going. Now, the last thing we need to talk about is securing OSPF, because one of the big problems that you could run into is that you accidentally form a neighbor adjacency to someone that you didn't mean to, or you actually are wide open to anyone who knows the parameters to form an adjacency and inject bad routes to you. Using things like passive interfaces as well as hashed authentication, we can actually create a secure OSPF authentication domain. Pretend for a moment that R3 is what is actually connected to our ISP, or our internet service provider. And we want this link right here to be advertised into OSPF. How do we do that? Well, we've already covered it. We could run the network statement, or we could run the IP OSPF process number, area number on the interface. But what's the real problem with that? We start sending hello packets out this interface too, and the ISP, we could actually end up forming an adjacency to the ISP accidentally. That's no good. We don't want to do that. So if I were to jump onto the console of router 3, first of all, I'll go into Ethernet 01 and give it an IP address real quick, something like 10.10.55.1, 255.255.255.0, and that's what I want to inject into my OSPF domain, but I don't want to send hello packets and form an adjacency on Ethernet 01. So what I'm going to do is I'm going to go into router OSPF, I'm pretty sure I called this 49, and the command that I can run is passive interface, and then we can simply specify which interface do we want to be passive. I'll say Ethernet 01. Basically, what this is saying is this interface can participate in OSPF link propagation, but it will never send out a hello packet out of that interface. Therefore, an adjacency will never come up on that interface. Now I can specify my network of 10.10.55.0, 0.0.0.255, area 1. And if I look on R2, I can do show IP route. Sure enough, I see the route right there listed as an OSPF learned route. If I jump back to R3, this part's pretty important. Let me exit out of this and say show IP OSPF interface brief. Check it out. I see that this interface is up and running while this interface is in a down state. That's because the passive interface statement has told this interface not to actually operate. So this is the first way that you could actually secure your network, is by just telling it we can share links through OSPF without actually propagating hello messages. But now let's take it up a notch, and let's say that we want an adjacency to only come up when we have matching passwords. We can actually send hashed algorithms back and forth to each other to make this happen. So let's take a look at the diagram real quick. What we want to have here is we're going to first deploy the MD5 password on Ethernet 01 and Ethernet 00. Huge talking point. The authentication in OSPF only takes place on specific links. So we have to specify this on a particular link where we want OSPF authentication to take place. So since I'm on R3, I'm going to go into configuration mode first. I'll say interface Ethernet 00, and I'll say IP OSPF. And the first thing we're going to specify is the actual key that we want to send. This is going to be an MD5 hashed key. So my message key, we're going to specify key 1. This is going to be our first key. It's going to use the MD5 algorithm, and I'll say something like Cisco rocks. That'll be the actual password that we're specifying. Now we need to turn on OSPF authentication. We'll say it's going to be message digest, and just press enter. At this point, this says we're going to be using MD5 authentication with the MD5 key that we specified on this particular interface. In a few seconds, we'll see that the OSPF adjacency comes down because the authentication doesn't match. If I say show IP OSPF neighbors, 1 second left, 0 seconds, and there it goes. The dead timer has expired because the hello packets were now transmitting an MD5 key within it that's like, wait a minute, the other neighbor doesn't have this MD5 key and we're not coming back to life. So on the other side, I can go into interface Ethernet 01. I'll say IP OSPF message digest. We'll say for key value of 1, We're going to use the MD5 algorithm to specify Cisco rocks, and we'll turn on IP OSPF authentication for message digest. At this point, the authentication should be coming up, and the OSPF adjacency goes from loading to full one more time. Now that's using the MD5 algorithm. We can take it a step further and actually use HMAC SHA now as another authentication algorithm, which also leverages the power of keychains. Keychains, we can do things like rotating passwords. We can set the expiration date of a password and the new start date of a new password. Keychains are very powerful, and this is again a topic that comes up in the CCIE exam. So if I go into configuration mode and I go into interface Ethernet 01, I'll say no IP OSPF message digest key, and I'll say no IP OSPF authentication message digest. Now from configuration mode, I'm going to create a keychain called OSPF. I'll specify for my first key of key 1, and then I'll say my cryptographic algorithm is going to be HMAC SHA. Let's go with 256 just for fun. The key string will be Cisco rocks one more time. So we've created the keychain, we've identified the key, we identified the cryptographic algorithm, and then we identified the actual key string itself that's going to be used as the password. Now when I go back to interface Ethernet 01, I can specify IP OSPF authentication. I'll specify my keychain, which we called OSPF. On router 3, I'll go into interface Ethernet 00. I'll back out the OSPF authentication that we did earlier, as well as the message digest key. And now I'll create the keychain OSPF, specify key 1, the cryptographic algorithm of HMAC SHA 256, and the key string of Cisco rocks. Just for fun, and so that you can experiment because you are the intellectually curious, the accept lifetime specifies how long we'll be willing to accept someone sending us a matching key like this, and the send lifetime specifies how long we'll be willing to send a key like this. This is how you can actually go about creating the rotating keys within a keychain to be used by OSPF. So now that we have the keys in place, I'll exit out of this and go back into my interface, which was Ethernet 00. I'll specify IP OSPF authentication, keychain of OSPF, and in just a second, we'll see the OSPF adjacency come back to life, this time using the cryptographic algorithm of HMAC SHA 256. There we go. So that's how we can go about securing our OSPF domains using both passive interfaces as well as encrypted algorithms containing a password. I hope this has been informative for you, and I'd like to thank you for viewing. So there you have it. That's OSPF, the inner workings of OSPF, and how we can design our OSPF areas or domain with all of these factors in consideration. We can understand the LSA types now and how that could be used in order to design our different areas. We understand the different area types like stubs or total stubs or not so stubs. Those types of things are also going to be a big deal when it comes to controlling the scale of our network and how the SPF algorithm is calculated or the LSAs are floated throughout the network. Beyond that, we also talked about authentication using the different hashing algorithms. So if you want to dig more into how to actually deploy these in the network, I'd really encourage you to dig into the Encore or especially the NARCI content here on CB2 Nuggets. For now, that's been OSPF Design. I hope this has been informative for you, and I'd like to thank you for viewing.